What if I told you we could send medicine directly to a diseased cell, almost like a tiny programmable drone? Well, today we're diving into a revolutionary piece of nanotechnology that does exactly that. And trust me, it's changing the future of treatment as we know it. Just think about this for a second. Instead of flooding your entire body with a powerful drug just to fight a disease in one little spot, what if you could package that medicine up and send it directly to the problem cells? And I mean, only the problem cells. What would that change? Oh, it would change pretty much everything. Well, the answer to that question is this incredible little thing, the liposome. You can really think of it as a microscopic delivery drone for medicine. It's made from materials our body understands, it's biodegradable, and it's basically designed by nature to navigate our system and drop off its cargo with incredible accuracy. So how in the world do you build one of these magic bubbles? To really get why they're so powerful, we've got to look at what they're made of. Turns out the secret is all in one very, very special kind of molecule. Okay, so the building blocks are these molecules called phospholipids, and they have this unique property called amphipathic. I know, it's a bit of a mouthful, but all it really means is that they have two faces. One part, the head, absolutely loves water. It's hydrophilic. The other part, the tail, hates water. It's hydrophobic. And this little love/hate relationship with water, that's the secret sauce. So here's our little building block, a water-loving head and these water-hating tails. Now, when you put millions of these into a water-based environment, like our bodies, something pretty amazing happens, completely on its own. Instantly, they start to organize themselves to protect their tails from all that water. They line up, tail to tail, and form this flexible, double-layered sheet where all the water-loving heads are facing outwards. It's just a natural defense mechanism. And then, to make sure there are no exposed edges at all, that sheet just curls up and seals itself into a perfect hollow sphere. And boom, just like that, you have a liposome. It's the perfect container. You can hide water-soluble drugs in its watery center, and you can even tuck fat-soluble drugs away inside that fatty wall. It's brilliant. Now, while this self-assembly is a totally natural process, making them for medical use requires an incredible amount of precision. You can't just, shake them up in a test tube. This is a serious nanoscale manufacturing challenge. Today, the state-of-the-art method uses a technique called microfluidics. So imagine a tiny channel where you shoot a stream of lipids that are dissolved in ethanol. At the same time, two streams of water come in and squeeze it from the sides. That's called hydrodynamic focusing. As all these liquids mix under these super controlled conditions, the phospholipids just snap into place, forming perfectly uniform liposomes. And the reason this method is so great is that it gives scientists incredible control. They can literally dial in the exact size and structure they need, which ensures every single liposome is consistent and high quality. And that precision isn't just cool science. It's absolutely essential for making medicines that are both safe and effective. So why is all this such a game changer? What's the big deal about wrapping a drug inside a tiny bubble of fat? Well, the advantage is huge. Let's talk about chemotherapy for a second. It's a powerful tool against cancer, but it's kind of like dropping a bomb on a city just to hit one building. Yeah, it kills the cancer cells, but it also damages healthy cells all over the body. And that collateral damage is what causes all those awful side effects. Liposomes, on the other hand, are like a targeted missile. The difference here is just night and day. A conventional drug goes everywhere, causing high toxicity, and our body breaks it down really fast. But a liposomal drug? It can be engineered to find specific cells. That little bubble protects the drug from getting destroyed, which makes it much safer. And it acts like a slow-release capsule, delivering a sustained therapeutic effect right where you need it most. And I want to be clear, this isn't some futuristic idea we're hoping for one day. Liposomal drug delivery is already in clinics right now, saving lives and dramatically improving treatments for patients today. Just take a look at Doxil. It's a liposomal version of a chemo drug called doxorubicin. This was the very first liposomal drug approved by the FDA, and get this, all the way back in 1995. It's used to treat several types of cancer, delivering that potent drug way more effectively while also reducing its famously harsh effects on the heart. And that's just one of many examples out there. But cancer treatment was really just the beginning. The incredible versatility of these little delivery drones means their potential is almost limitless. We're seeing them stretch into all sorts of fascinating new areas of medicine and even beyond. For real, this same technology is being used to make vaccines more effective and more stable.
In nutraceuticals, they're protecting delicate vitamins and nutrients so they survive our digestive system. In cosmetics, they help active ingredients get deeper into the skin where they can actually work. And maybe the most exciting of all, they're becoming a key vehicle for gene therapy, carrying the genetic instructions needed to fix diseases at their source.
So, from cancer to cosmetics, from vaccines to vitamins, the liposome is this incredible platform that's making medicines smarter, safer, and a whole lot more effective. And it leaves us with a really exciting question to think about. With a delivery system this precise, what massive medical challenge should we aim it at next?